In example 1, we saw how ramping the current in a solenoid resulted in a changing magnetic flux in the solenoid that produced an electric field intensity. If the ramping current produced an increasing magnetic flux in the z direction, if you look through a cross section of the solenoid, so here's the cut through representing the solenoid, the resulting electric field intensity are circles around the solenoid. In example 1, the current in the solenoid was ramped at a rate to produce an electromotive force of 6 volts, so that the magnitude of the electric field intensity was 6 over 2 pi rho volts per meter, where rho is the distance from the center of the solenoid. In example 2, we put a conducting material that had a total resistance of 6 ohms that was in the form of a ring around the solenoid. With the solenoid producing an electromotive force of 6 volts, the result was 1 amp of current flowing around the conducting ring. Again, let's surround the solenoid with a conducting ring, but this time the ring will be made out of 2 materials. The material on the left will have a higher conductivity than the material on the right, such that if you measured the resistance of the half ring to the left between this point and this point, you would get 2 ohms, and if you measured the resistance of the half ring to the right between this point and this point, you would get 4 ohms. Let the current in the solenoid be 0 for time less than 0, and for time greater than 0, ramp the current in the solenoid at a rate to produce an electromotive force of 6 volts. So at t equals 0 plus, just after the current is ramped, the electric field will be circles surrounding the solenoid of value 6 over 2 pi rho volts per meter, where rho is the distance from the center of the solenoid. So at t equals 0 plus, the electric field intensity in the half ring to the left and the half ring to the right will be the same, but because of the different conductivities, the current flowing in the half ring to the left will be larger than the current flowing in the half ring to the right. So at the boundary between the left and right rings at the top, there's more current flowing into the boundary than away from the boundary, so it will start to charge up positively. At the boundary on the bottom, there's more current flowing away from that boundary than into that boundary, so there will be a net buildup of negative charge. This charge buildup will result in additional electric fields emanating from the positive charges at the top boundary and terminating on the negative charges at the bottom boundary. In the left half ring, the electric field intensity coming from the positive charges and terminating on the negative charges will be in the opposite direction of the electric field intensity coming from the changing magnetic flux in the solenoid. So the electric field intensity in the left half ring will be reduced as the charges build up at the boundaries. In the right half ring, the electric field intensity coming from the positive charges and terminating on the negative charges will be in the same direction as the electric field intensity coming from the ramping magnetic flux in the solenoid. So the electric field intensity in the right half ring will increase as the charges build up at the boundaries. As the electric field intensity in the left half ring is reduced, the current will reduce in the left half ring. And as the electric field intensity increases in the right half ring, the current flowing in the right half ring will increase. The current in the left half ring will reduce and the current in the right half ring will increase until the two currents are equal. When the two currents are equal, there is no longer any change in the charges at the two boundaries, and steady state is reached. Let's apply Faraday's law to a clockwise path through the ring. The integral of E dot dl through the left half of the ring will be the current flowing in the left half of the ring times 2 ohms. And the integral of E dot dl through the right half of the ring will be the current flowing in the right half of the ring times 4 ohms. And this will equal our electromotive force of 6 volts. Since in steady state the current in the left half ring is equal to the current flowing in the right half ring, the current flowing around the ring is 1 amp. So in steady state we'll have 2 volts dropped across the left half ring and 4 volts dropped across the right half ring. So summing the voltage drop around the ring will give us 6 volts, which is equal to the electromotive force coming from the solenoid.